Okay, welcome back to our little garage studio. Today we're talking about classical statistical mechanics, where I am condensing down to the information that you already have in the notes, just to give a little bit of a structure. And so we will quote some important results, derive a couple of things, make some shortcuts, but ultimately identify a couple of important quantities. Okay, so we are talking about classical statistical mechanics. What do we mean by that? We mean that instead of having our system obey quantum mechanics, the appropriate mechanics that will govern the motion of the system that we want to investigate are classical, so Newtonian, right? That's what we mean by the term classical in this class. Newtonian means that mass points or particles can have a well-defined position and a well-defined momentum, unlike that in quantum mechanics, where the Heisenberg uncertainty principle prevented us from knowing those two with infinite precision. In the classical Newtonian world, there's nothing wrong with that. And so you can specify the simultaneous position and momentum of a particle and not there are no issues with that whatsoever. The law of motion that describes the way particles move is not the time-dependent Schrodinger equation as it is in quantum mechanics, but it's Newton's second law of motion, right? It's force equals mass times acceleration, where the force is a vector and so is acceleration. And so that's what we want to talk about. Now, why do we want to talk about classical mechanics? If we know that quantum mechanics at its root governs behavior of all matter, why is the classical mechanical limit an important one to explore and to talk about the statistical mechanics thereof? The primary reason is that it is frequently the case that quantum behavior goes over smoothly into the classical behavior, and the classical behavior is sufficient to understand the physics of the system. For example, it is completely reasonable to understand liquids to first begin to imagine that your liquid particles are not quantum mechanical particles, but are classical particles subject to Newton's laws of motion. That's already a complicated enough problem, and so you perhaps may want to investigate that problem before you investigate the quantum mechanical analog of a liquid state. It may also be more mathematically tractable, perhaps. Sometimes that is the case for a classical mechanical system, and so it is a very important limit of quantum behavior and frequently a very good approximation for the behavior of a system. And of course, the classical behavior will fail in certain respects. What is the main change for us when we're speaking about a classical mechanical system? A system that is allowed to have a well-defined position and momentum, or particles that are allowed to have well-defined position and momentum. Well, so for a classical state of a one-particle system, let's say in a box. Suppose you have a box. And you have a particle that has some mass. It has some position. Oops, let's call this y. Right, this particle has some position, perhaps denoted by the position vector r. And it has some momentum. We can denote by this vector, momentum vector p. Kind of drew it too close to the box. Momentum vector p. And so this is the state of a classical mechanical system that is composed of just a single particle. You specify its position, you specify its momentum vector, so position vector, momentum vector, at some point in time. And that's the instantaneous classical state of the one-particle system. Now, in the next instance in time, this particle will move in the direction of its momentum vector, particularly if it doesn't collide into anything along the way. And so in the next instance in time, the classical state of the particle will change. What about a multi-particle state? What if you had two particles? Well, this particle might be traveling there. Its position vector is here. Let's call this maybe R1 and R2. Perhaps this is M1 and M2. Maybe there are different particles with different masses, maybe the same mass. And so this is the classical mechanical state of the two-particle system. So for two particles, classical state of the system is specified by providing the position and momentum coordinates, of both particles. Position and momentum coordinates of two particles, right? For two particles, the classical state is specified by providing 6 numbers: x1, y1, z1 for the position of particle 1, and the x component of the momentum vector for particle 1, the y component of the momentum vector for particle 1, and the z component of the momentum vector for particle 1. That's for the first particle. And now, particle 2 is at position x2, y2, z2 with momentum px sub 2, py sub 2, and pz sub 2. And so the classical state is specified by specifying the position, the instantaneous position, and the instantaneous momentum of both particles. For an n-particle system that has many particles, right? In our class, its n has been of order 10 to the 23rd. The classical mechanical state of a many-body system with n particles is provided by stating where each particle is, what its momentum vector is at some point in time. And of course, the implication of that is that time goes on, the state of the system changes. Why does the state of the system change? It changes because the position of each particle and the momentum of each particle is changing. For example, at this point, this particle might bounce off the walls and be flying in a different direction. So its momentum vector will change. Of course, each particle is moving through space, so it's continuously changing its state just by changing where it is located in space. And you can easily generalize this to an n-body system. So that's a classical mechanical state. Now, our business with statistical mechanics has been to calculate average values of macroscopic systems. For example, the average value of the energy of the system, or the average value of the volume, and so on. The average value of the pressure. And so we know that to calculate average values, you must have the probability distribution. The probability distribution for what? For the system to be found in some specific state. In quantum mechanics, that state was a quantum mechanical state. And we talked about microstates as the many-body quantum states of a many-body system. Here we have a classical mechanical state where for an n-particle system, you're specifying the instantaneous position and momentum for each particle. And so the states of a classical system are not discrete, right? In quantum mechanics, when we solve the Schrodinger equation, we get an infinite number of solutions, but they can be counted as integers, right? They follow some quantum number that increases in magnitude by integral values. For example, n equals 1 and n equals 2 and n equals 3. The states were quantized, right? The particle couldn't have any possible energy. It had to be any one of the quantized sets. The particle also couldn't be said to possess a specific momentum and to be in a certain place, a certain point in space with infinite certainty. Whereas in classical mechanics, that's exactly what we're saying. And so the probability distribution that we are after is going to look a little bit different. And here's why. In quantum mechanics, we said, what is the probability that the system is going to be in this microstate? Microstate J, microstate 37, and so on. And we had this discrete probability distribution. And you could label the number of microstates with some index that ran from 1 to infinity, changing by integral values. In classical mechanics, that's not true because the state of the system is changing continuously. There is a continuum of possible positions, a continuum of possible momenta. The energies are no longer quantized. And so the momentum of the particle can be anything in principle. And so the states cannot be counted with integer values. The mathematician would call this set of states, or the set containing an uncountable infinity of states. You can't count them. The numerical values that describe the state of the system are real numbers, not integers. And real numbers are extremely dense. And so it stops making sense to ask for the probability that, let's say, particle M1 has position here and this momentum. Why does it not make sense to ask for that probability? Because around this specific position, there will be a dense infinity of many other positions. And when you say, what's the probability that my particle is found with an x-coordinate of 1.037495, and so on, the probability will always be 0 because the particle will never be found at the exact position that is described by the real number that you're asking about. And similarly for the momentum. And so we have to modify our notion of questions having to do with probability relative to the quantum mechanics that we've done so far. However, you're familiar with this. And the reason why you're familiar with this is because you already had to pass a quantum mechanics class to get to this course. And in quantum mechanics, you dealt with with probabilities that depended on continuous variables. That probability had to do with the wave function. Right? We know that the square of the wave function was the probability density to find the particle in some small region, somewhere in space around a small region. So we have to remember back to those ideas of how we talked about probability density and translate it to what we're talking about now. So let's revisit that. What happens when you have states that are described by a continuous variable, not a discrete integer, not a discrete index? And so what I'm saying, let me get the right notes. In quantum mechanics, we had a probability to be in some microstate J. And that the system could be found in any one of its possible microstates J, but J was a discrete index. And we had a normalization condition that said sum over all possible values of J, where J labels the microstate, of these probability values. And if they are true probabilities, they will be normalized. But because our variables, x and p, position and momentum, are continuous, as I just mentioned, we can't do that. And so we speak classical mechanics, Newtonian mechanics. We say, or we modify our question, and we ask for what is the probability, and let's do this for a single particle, the probability that our particle has position not equal to x, y, z. That's not the question we're going to ask. Not that it has a very specific position given by the real number x, the real number y, and the real number z. We are going to ask for the probability that the particle has position in the small interval dx around the point x. In the small interval dx around, let's say, some specific point x naught, and momentum, doing this for a one-dimensional particle to keep it simple, and momentum px, in the small range, in the range dpx around some point px naught? That's the question that we're asking. We're not asking for the probability to be in a specific position x naught. The probability of that would be 0 for any given x naught because, as I mentioned before, the points are infinitely densely close to each other. Around any x naught, there's an infinite number of other x values that differ infinitesimally from it. And similarly, we're going to ask that the momentum is centered around this value, but we're not going to force it to be exactly this value. We're going to say in some small increment around this value px sub naught. So roughly to an infinitesimal region dpx around the point px naught. And of course, because this is infinitesimal, this interval lies intimately closely around that point. And so for the probability, we're going to have a quantity that looks like, I'm going to draw p hat, or I'm sorry, p bar, depending on x naught and px naught times dx times dpx. This is the probability that the particle has momentum, or that the particle's momentum is in a small interval dpx around the value of momentum px, and the particle's position is in a small interval dx around the point x naught. And so notice that the probability value has the interval in it. And so the value of the probability, this whole thing, depends on the interval itself and is in there, must be included. This quantity is the probability density. Or set in words, the probability per unit interval in x and per unit interval in dpx. So that if you know this number, the probability, what's the probability to be in a given increment? You then multiply that by the value of the increment, the length of the actual increment, and the product of the two gives you the probability that your px is somewhere in this range and x is on somewhere in that range, around the point x naught. And so this is the probability density, whereas the whole product is the probability that answers that question. What examples have we seen of this probability density? Well, the wave function. Depended only on position. Where in quantum mechanics, this was the probability that the particle is found somewhere near the point x naught in an interval dx. So the exact same idea. Except there, what emerged from this analysis is that the states had to be quantized. Right here, I just want to make sure that this is kind of a confusing point. Here, x was not the state of the system. Remember, in quantum mechanics, you can't specify the position of the particle and momentum with infinite precision. This was the variable on which the wave function depended, but the wave functions themselves were labeled by an integral values, right? So to each quantum mechanical state, there was some specific wave function associated with it. And when we solve the Schrodinger equation, we get an infinite number of these solutions, these wave functions. But n was 1 and then 2 and 3 and so on, right? The wave functions themselves were quantized, even though the wave function is a function of a continuous variable. Here we're saying the states themselves are labeled by continuous values. Here the states are labeled by a discrete integer. So I know it's a little bit confusing, but I hope that clarifies a little bit. But nevertheless, you've seen the probability density before, and now we're seeing it again. And so what does the normalization condition look like for a classical particle in one dimension, moving in one dimension? So normalization condition for a classical particle Classical particle free to move in one dimension only. Able to move in 1D. So if it's a single particle and it's moving in one dimension, then only two numbers need to be specified to specify the classical state of this particle. The instantaneous position, the instantaneous momentum only in the x direction. That's all it can do. And so the normalization condition is not going to look like a sum. Why is it not going to look like a sum? Because we have these infinitesimal elements. And so the normalization condition is going to look like this. I'm just not going to drop the x naught and p naught and just write as x and p sub x integral over dx integral over dpx. Now remember, in the quantum mechanical version, the sum was over all possible states of the system. Here, we don't have a sum, we have an integral over all possible states of the system. All possible states of the system usually will be x from minus infinity to infinity, and px from minus infinity to infinity. And so I should have two integrals actually here. So this should go minus infinity to infinity for x and minus infinity to infinity for dpx. All possible values of position, all possible values of momentum. This quantity is going to be equal to 1. That's the normalization condition. Remember that the integral is nothing more than the limit of a sum. Right? The integral is the limit of terms that look like this, where you go from one point in x to the next, to the next, to the next, changing from one to the next by a small interval dx. And so, in a sense, this integral masks the fact that it is very much a sum like that. It's just a sum in the limit as these guys become infinitesimal. If they were not infinitesimal, if they were finite for some reason, you would have a sum from one value of x to the next by delta x, to the next by 2 delta x, and so on. But into the infinitesimal limit, which is what we mean, the sum becomes the integral. So this is the normalization condition for a classical mechanical system. Now, this immediately tells us how to calculate average values of our system. For example, suppose you want to calculate the average value of x. Or actually, before I do the average value of x, suppose you want to calculate the average energy, for example. Now, the energy of a classical mechanical system gets a special name. Energy of a classical system, i.e. a system that follows Newton's laws and not Schrodinger's equations. Energy of a classical system is called the Hamilton function. The Hamilton function. The Hamilton function, the classical Hamilton function, usually given the symbol h, of course you'll recognize it as the Hamiltonian in quantum mechanics, which is the quantum mechanical extension of the classical Hamilton function. And by the way, I should say the total energy of a classical system is called the Hamilton function. This quantity depends on, if it's a one-dimensional particle, the position and the momentum of the particle. So the classical energy reflects the instantaneous state of the system. The classical energy is the kinetic energy plus the potential energy. The kinetic energy is px squared over 2m, which is the same thing as 1/2 mvx squared. And you can prove that to yourself by noting what px is. Plus the potential energy, I'm going to call it u, which will depend on the spatial coordinate x. So that's what the classical total energy looks like. It always depends on both the momentum and the position variables. Almost always, for systems that a chemist will care about, the potential energy depends only on x, not px. The kinetic energy will depend only on px. And so the kinetic energy term depends on px only. The potential energy term depends on x only. So the classical energy, if we wanted the average value of the classical energy, let's remind ourselves that it depends on these variables. What we would do is we would integrate over all space and all momentum values, or sum over all the quantum states, if this was a discrete system, of the classical energy as it depends on position and momentum, and you can plug it in if you want, times the probability that the particle has position in the small interval dx around the point x, and that the particle has momentum px in the interval dpx, dx, dpx, probability density. This is the probability that the particle has position in a small interval dx around the point x and momentum in the small interval of values dpx around the value of momentum px. Both of these factors, the probability density, the probability per unit interval in x and per unit interval in px, times the length of the interval in x and the length of the interval in y, times the value of the classical energy as it depends on position x and momentum px. Integral over all space in x and px, i.e. a sum over all the quantum states, or in this case classical states of the system. That's the prescription. What if you wanted the probability that the particle has, what if you wanted the average position of the particle? The average position of the particle free to move in one direction, one dimension. Well, the average position is the same prescription, probability or integral over all space over position variables and momentum variables, times the thing you want to average, so in this case it's just x, not something that depends on px also, times the probability density, x, px, dx, dpx. So you would do a similar integral for the value of px. Now notice something interesting here. The integral over x depends on x obviously, but the integral over px does not depend on this variable x. So what if we perform the integral over dpx first? What if we wrote this out like this? Integral over minus infinity to infinity over dx times the value of x. Now, times the value of dpx of the probability that the particle's momentum and position are around this point, dpx. Notice that dx went along with this integral, and here I'm integrating only the probability that the particle has some momentum. Notice that in this integral over dpx, x is a constant. And so it's as if for a given x, this integral is being carried out over all possible dpx. So this is an integral over the probability density, or, as we talked about, the sum over all possible values of the probability with x fixed in some position, but momentum varying from all possible values of px. What do we expect from here? We expect that when we integrate over all dpx, the probability that the particle has some momentum in px independent of x should be normalized. And so when we integrate over this probability, what we should end up with is the probability that the particle has some position x regardless of what momentum it has. So we are summing or integrating over all the possible values of px for a given position. And that probability ought to be normalized. And what you should end up with is just the probability that you have the particle having position x independent of its probability in momentum. And so what this thing should look like is, let me rewrite this, probability to be, or the average x should look like integral over from minus infinity to infinity over dx times x. Now the result of this integral is the probability that the particle has some position, or the probability density that the particle has some position x independent of the value of momentum. The reason being that we have integrated, or we have summed over all the possible values of momentum. And because the particle has to have some momentum, or the momentum values are mutually exclusive and exhaustive in our language of probability, then the integral over all possible values of momentum of the probability density, with x now being viewed as a constant, should be 1. And the result of this is just the probability that the particle has position x independent of what the px is. It is no longer a function of px because px has been integrated over or summed over. And so in this question we are saying we don't care what the probability, what the specific momentum of the particle is. We just want to know what the position of the particle is for all possible momenta. And so now this is replaced by just the probability density to have position px. And so even though the probability density is a two-dimensional function for a single particle in one dimension, when you want the probability of x, the integral over dpx, because the probability density is normalized for the px, gives you a quantity that looks like only depending on x. And you will find that the similar expression should be found here. Integral now over all possible momentum values of dpx times the value of the momentum times the probability density that the particle has some momentum px regardless of what position it has. So in that case, the integral would be over all possible positions, and because that probability density is normalized, that's what you end up with in this case, just like in that case. And so that's how one works with classical or continuous probability distributions and how one can find the average value of anything. And of course, this is in the general case, the average value of some function of x and px is found with the exact same algorithms of what we've been doing for discrete probabilities, except now our probabilities have become continuous functions of the variables on which they depend. And so using these continuous probabilities and these methods of finding average values, we're going to go on and work with the classical probability distributions.